Okay, welcome to the next lecture. This is a momentum equation examples. So I think I have three or four, I think I have three examples of solving the momentum equation. And one thing we need to remember as we work on this momentum equation, so today what we're going to do is we're going to basically solve problems with it, make sure we know how to do that. So what I want to remember here is that we've got some tools that we want to work with. These are the tools. We're going to kind of move these around. I have another copy of that somewhere so we can use it again. And here's the first problem. So we're going to jump right in. Example 1. This is a vertical bend, which means that this 2 feet that I have drawn here, that's a vertical 2 feet. So like in all of my problems, I like to make z upwards, and I guess x will be forward. And we've got some things that we need to know. We know that this is a... we don't know a V2 yet, so that shouldn't be labeled there. Sorry about that. Okay, we know the diameters of the pipe, so we know phi1 is 2 feet, phi2 is 1 foot. Sometimes you'll see capital D. Usually you'll see capital D, but on this problem it was phi. Alpha is 45 degrees, so basically as the water comes in through that pipe, it turns upwards at 45 degrees. The flow rate is 15.7 cubic feet per second. P1 is 21 psi. We don't like psi because everything else in this problem is in feet. So let's go ahead and convert that. If you don't know how to convert that, I highly recommend you figure out how. Basically in this, nope, sorry, not that one, psi. So basically we're going to convert it by multiplying by 144 square inches over square feet. And we're going to get 3024 PSF. Okay, that's a much better unit to work with. And then... let's see, so then we've got the mass of the bend. So that's the mass of the pipe itself is 1,000 slugs, which is obviously, well, maybe it's not obvious to you guys, but to me, that is very definitely a massive number. Generally speaking, so if a slug is 32.2 pounds mass, this is a 32,000 pound bend. Okay, that seems kind of big for something that holds 10 cubic feet of water. Okay, so there's 10 cubic feet of water in there. All right, so then what we want to do is we want to find the force of the water on the bend. So as this water passes through here, right, it's being turned by the bend, right? Otherwise, it would just keep going straight, but instead it's turning, and in fact, it's accelerating, right, because the pipe is narrowing. So as it does that, the bend is causing it to do that, and so the water is pushing back, right, by Newton's third law, equal and opposite reactions. So what we want to do is we want to solve this. And this one's problematic. So we've got a bunch of tools over here that we can work with. But what I'm going to suggest to you is that right now we already know what we're doing here because it says find the force of water on a bend. Anytime you have a force of a fluid and the fluid is moving, you need to use this momentum equation. Okay, so that's kind of going to be our master. But unlike when Bernoulli is our master, what I'm going to do is I'm going to draw a free body diagram of, well, we want the water on the bend. So what I'm going to do is I'm going to do a free body diagram of the water, okay? And sometimes it should be the water, and sometimes it should be the water and what's holding it. In this case, it's the water because I'm directly curious about this. Sometimes if you want to know the force required to, let's say, hold up the bend, then you want to include the bend in there as well because then the free body diagram will have that as kind of what you're solving for. And we'll do that on the next one. But right now for this one, we're doing a free body diagram of just the water. Okay, and luckily, drawing a free body diagram of the water is, it's almost like I'm just redrawing what's above it. And yes, I do expect you to redraw it because it doesn't really take all that much time. Look at that. That wasn't very hard, was it? All right, so now what we want to do, so this is my control volume, right? So here's my control volume. I'm drawing it kind of in blue. Okay, so what I want to draw on this control volume, anytime I'm working with the momentum equation, is everywhere where there's a momentum flux. Okay, so here's volume 2, so that's a velocity 2, excuse me. That is a flux of water or fluid that is crossing the control surface. Okay, I have one here as well, V1. Okay, otherwise, all I have is a bunch of forces. Okay, what forces are acting on this water? Well, we've got a body force, which is the weight of the water, right? The weight of the water. And we've got all kinds of frictions and things along those lines, right? So, like there's a friction on the walls and you know, there's normal forces and things like that. But you know, we don't want to parse all those out. We're just looking, you know, we're just going to call those all. So I'll call this force. Let's see, bend on water X, Baux, and this will be force Bowie, bend on water in the y direction. Okay, so what we've done by doing that is, you know, all those other forces, ways the bend pushes on the water or pulls on the water or slows it down or whatever, are just encompassed into those F's. Okay, and then do we have any other forces on this water? Okay, we got the body force, the weight. We've got these two ways to bend. What else? Okay, at this point, I can understand if you missed it, but you should. So you see the way that I drew this right here and here? That means, oh, geez, what is that? Let's undo that. Or maybe we'll just grab it and move it out of here. Okay, you go over there, punk. All right, let's try that again. All right, so you see the way that I drew these? I drew this one and I drew that one. Okay, those little things means that this pipe is not open to the atmosphere. If it's not open to the atmosphere on those edges, like I'm just not drawing the rest of the pipe, it means there's pressure in those points. So there's a pressure, and pressure always pushes. Okay, so pressure looks like that. Okay, and pressure looks like this. Okay, so those are forces on this thing. So this is going to be P1A1, and this one right here will be P2A2. Okay, so now we have all of our forces on the fluid, unless there's some others that I've forgotten, but you know, that would surprise me. All right, so anyway, so what we need before I start playing with the momentum equation is I want to work with my other tool. So when we do Bernoulli, normally you know, the way that I've kind of worked it is I just kind of start working with Bernoulli and see what I need. In the case of the momentum equation, all of those things, these are what I need to, what's the word? I need to hash out. So I need to know what each of these things are. So I need to know P1A1, I need to know V1, I need to know V2, and well, I'm looking for these two, the bow X and the bow Y's. Oh, before I continue, what about the mass of the bend? How come I didn't include that? The mass of the bend is 1,000 slugs, and I didn't include the weight of the bend. And here's why. It's because the bend itself is being held up by something else entirely, and the weight of the bend is not acting on the water. The water is not holding up the bend. Okay, so there's no reason to include the mass of the bend. The bend could get 10 million times bigger, and it's not going to show up in this problem. Okay? Anyway, so let's go ahead and start solving for things. Let's see here. P1A1. Well, let's see. We have P1. Let's kind of make a list. Well, let's start with pressures. Okay, P1A1. Okay, what do we need for that? Well, we need A1, right? So let's say A1, that means we're going to need A2, right? So that's going to be pi times that diameter, 2 feet. 2 feet squared over 4. So basically that's going to be pi square feet. And then A2 is going to be pi times 1 foot squared over 4. So that's pi over 4 square feet. All right, so we've got those areas. What about P2? Do I have P2? P1 is given, but there's no P2. Right, it's not given. Okay, what my students typically do in this case is they like to assume P2 is 0, and then they lose points. Okay, what's a better way? Any thoughts? Okay, the better way to do is to look at your tools. Okay, normally how we get at pressures is we use a manometer, but there is no manometer in this equation, so we can go ahead and like knock that one out. What do you think we should? How about we look at Bernoulli? That's my other way to get at pressures. Okay, the geometry does not have pressure in it. Continuity does not have pressure in it. Momentum has pressure in it, but usually you don't back calculate momentum out of that. Okay, so let's go ahead and do Bernoulli. Okay. All right, so here we go. Let's zoom in a bit. This is we're a little far out here. Okay, so I don't want this to be an equal sign because it's not an equal sign. Okay, so how are we going to solve for this? Okay, so P1 is given. It's 3024, I believe, right? So we'll say 3024 PSF. It's awfully nice when PSF is over 62.4 PCF. Okay, so notice that's going to give us feet. Z1. Well, we need to decide where our datum is, so it seems to make sense to make this our datum. So Z1 will be our datum. So that's going to go away as our datum. Right, which means Z2 is going to be 2 feet, right? Okay, so this will be plus 0 feet plus what's V1? Well, dadgummit, we did this a little bit out of order. We need V1. Okay, so let's go ahead and let's get V1. I'll do it over here. V1 equals, well, V1A1 equals Q. Right? So, and this is how these problems get messy, right? So what I typically like to do is I pretty usually like to have an aside area. So I'm going to call this my asides. So sometimes what I'll do is I'll fold my sheet of paper down the middle, and I'll work the problem primarily on the left, and on the right, every time I realize I needed something, I'll just kind of go do that. And it looks like I'm kind of doing the opposite of that. So this is kind of the main problem area over here, and this is the asides. Okay, so let's see here. V1A1 equals Q. So Q is 15.7 CFS. Okay, A1, which is what we have solved for, is 3.1415 feet squared. And this is V1, right? So V1 works out to a nice, pretty 5 feet per second. It's almost like somebody designed this problem. Okay. Noting again, to get V2, I could follow the exact same procedure. I could say V2A2 equals Q, and I leave you to do that if you want. Or what I could note is that the area, the cross-sectional area of the pipe at 2, okay, by having a diameter of half of the diameter at 1, okay, it's got a cross-sectional area of a fourth, which means that the velocity is going to be 4 times as big. Okay, so 20 feet per second. Okay, or you can solve that if you want. Okay, but I'm not going to do that. Okay, so now we've got 5 feet per second squared over 2. Now what's g in this case? We have to think what unit system we're working in. So it's 32.2 feet per second squared. Okay, equals. Okay, now let's zoom in. Let's see here. P2. Well, that's what we're looking for. P2 over 62.4 PCF. Okay, plus 2 feet. Plus V2 squared on 2G. V2 was 20 feet per second squared over 2 times 32.2 feet per second squared. Okay, some things to note. Well, you know what? I'll show you these to you as we I'm not going to just jump to the answer. I'm going to go ahead and put in an intermediate step so we can talk about this. Plus 0.39 feet equals P2 over 62.4 PCF plus 2 feet plus 6.21 feet. Okay, so a few things to note. Okay, this pressure term is the most significant one by far. There was no way for me to know that going in. There's no way for you to know that. One thing that happens very commonly in these is that the change in elevation on a momentum problem is usually not very important. So usually if you've got like a nozzle or just some sort of bend in the fluid, a lot of times people will neglect this. Okay, they will just go, well, we're just going to pretend that it's like of negligible height. Okay, obviously in this class, if I give you that height, you need to use it. But if I don't give it to you, usually you can neglect it. Okay, so just be aware of that in the future. The other thing to note here is the velocity heads. Okay, notice these velocity heads. Notice how much larger this one is, okay, compared to this one. Okay, why is that? Well, and it's very simple, okay? So the nozzle, when I draw this nozzle like this, okay, this diameter is half of this diameter, okay, which means that this velocity is 4 times the velocity here, okay? And then that goes into the velocity head, that becomes 16 times the velocity head because you square it. Okay, so a lot of times, okay, when things shrink like that, you get, or when the cross-sectional area shrinks and everything has to go through it, a lot of times what will happen is this one matters and this one does not. Okay, so something, you know, so you could potentially neglect this. Okay, potentially. Okay, now in this class, please don't neglect those things, just because I'm testing to see that you can do all those things. But it's just something to, you know, be aware of. I don't know why it really wants me to play with that shape. Anyway, so we can solve for P2 at this point. It changed my color of my pen. Okay, P2 equals, what does it equal? 25.2536 PSF. Okay, now just because I convert that back into PSI, 17.6 PSI. That's just because. And that's just because I wanted to be able to look at this and say, let's see, what was my original PSI? It was 21. So the pressure drops to 17.6, going from here to here. And there's a few reasons for that. One, okay, why did pressure drop? Pressure dropped because one, Z went up. So we went upwards in this fluid, right? And just like in hydrodynamics, when you go up in a fluid, when in hydrostatics, when you go upwards in a fluid, the pressure is going to drop. Okay. The other reason that P went down was because the V went up. Okay. When the velocity increases, the pressure decreases. Okay. Generally speaking. Okay. Obviously, you could have a case where these two things could work against each other, and that happens all the time. But in this case, that's why the pressure dropped. We should have expected a lower pressure. Okay. Anyway, so let's go ahead and see what else we need. So now we look at we look over at our drawing over here. We have solved for our, let's see, we've got P1A1. We have solved for P1 and A1. We've got P2 and A2. We did not get the weight of the water yet. Maybe that's what we should do next. But we got both of the velocities. So we're ready to solve the momentum equation, really. So then the weight of the water, well, it's gamma times the volume of the water. So the gamma of the water is 62.4 PCF. Okay, and the weight of the water is, how much do we say? Excuse me, the volume of the water is 10 cubic feet. Okay, 10 cubic feet. Okay, so that makes for easy math. I don't even have to refer to my notes, right? 624 pounds. That's a lot of water. Or at least it's a heavy water. I don't know if it's a lot of water. I guess it's a pretty big bend. All right, so we're pretty much ready to go. Okay, so let's go ahead and solve this. We need the momentum equation. So I guess all of this stops. Well, we shouldn't have any more asides, but let's go ahead and do the momentum equation. Okay, because now we have solved for everything in our free body diagram. So I'm going to leave that out, leave that where we can see it the whole time. You know what? Let's actually erase something. I never really like to erase stuff. Let's not erase stuff. Okay, the momentum equation. Okay, sum of the forces in the x plus sum of, let's see here, how do I normally write it for you guys? Vx rho q in equals the sum out of Vx rho q. Okay, let's note that there is an x version of this, and there's a y version. Maybe I'll do the y version over here. Okay, sum of the forces in the y plus the sum in of Vy rho q equals sum out of Vy rho q. All right. So let's keep that free body diagram in mind as we look at the sum of forces. Okay, so I'm looking at the diagram now, and I'm trying to, or my free body diagram, and I'm trying to figure out what are the forces on this water. I've drawn them all. In fact, it looks like I drew them all in red. So I guess because I have the y equation on the left, we'll do that one first. So what forces do we have in the y direction? Well, let's see here. The P1A1 does not act in the y direction. F bow we is positive, minus the weight of the water, minus P2A2 times the sine of alpha, and the other y forces. No more y forces. Okay, so now we need to do the momentum fluxes, which I've labeled in blue up there. So I've only got one in, and that's the V1. So plus, but V1 is not in the x direction, in the y direction. So we'll go ahead and erase that plus and make it an equal sign. I don't have any y momentum coming in. I do have y momentum coming out, though. I've got V2. Okay, so now I'm doing this Vy. So it's V2 sine 45, okay, times the density of water, rho, times Q. Okay. I'll go ahead and set up the X direction as well, because at this point it's all plug and chug. Although I will make a point that a lot of you guys are going to want to use, for rho, you're going to want to use something other than 1.94 slugs per cubic foot. If you use something other than 1.94 slugs per cubic foot, you're going to get this wrong. Okay, I know you don't want to use slugs. I know you're avoiding it. I know you think somehow you're going to get through this class without it. You have to use it. Sorry. If you put in pounds right here, it's going to be wrong. Okay. All right, so we'll do the X direction. So again, my forces are all in red. So I've got P1A1 is in the X direction now. I've got plus force bend on water in the X minus, let's see, we've got the P2A2, okay, but that's not really in the X direction. So we need cosine 45. Do we have any more X forces? Those are all my X forces. All right, plus, okay, do we have a velocity going in? We've got V1 going in, and it is directly in the X direction. We've got rho, and we've got Q. Okay, we don't have any angles on that one. Equals, and then leaving, we've got V2, so that's going to be, sorry guys, V2 cosine alpha. Oh, huh. For some reason I put in a 45 down here. I didn't really want to do that. Let me go ahead and erase that and put in an alpha. Sine alpha. Okay, cosine alpha over here, and then rho Q. Okay, at this point it's plug and chug, but like I said, you have to remember that the density is rho, which is 1.94. Okay, so let's zoom in here and let's go ahead and solve these. I'll just kind of have the algebra pop up for you. Okay, so plugging it all in, the only kind of notes here that might create problems is remembering that this needs to be in PSF, okay, pounds per square foot, because we're working in pounds and feet. We're not working with inches here. Notice this area is in inches. The rho has to be 1.94 slugs per cubic foot. Okay, so if we plug all that in, F Bowie is 2463 pounds. I know I usually like to keep 5, but when I did this, I didn't have that rule. So I'm following my key right now. Okay, so that's how you solve that. And then we're gonna go over here. We'll do the same thing over here. Note again, there really isn't anything, if you can do the left-hand side, the Y equation, you should be able to do the X equation. But again, I'll just plug it in and make sure there's nothing unusual. Okay, and this side kind of stretches out, and so I recommend you kind of take a moment and make sure you understand where all these numbers come from. But there's nothing particularly scary or unusual about any of these numbers. There's just a lot of them. Again, you have to use 1.94 slugs per cubic foot. Okay, some of you are going to insist on using 62.4 pounds mass. Your book uses 62.4 pounds mass. I don't really understand why you would choose to do that, especially because it was not going to work. They're going to have to multiply by some weird number to make this work, and I don't know why you'd want to do that. Anyway, so the only thing that I will note here is that a lot of times what people will do, if you look at these two terms right here, you can see all these similarities, except for the velocity. So what a lot of times people will do is they'll rewrite this as V2 cosine alpha minus V1. Okay, so they'll kind of move this term over, this term over here and kind of combine the two terms and multiply that times rho Q. And you can certainly do that if you want, okay? It's not necessary. Anyway, so what we end up coming out of this is the force in the X direction is negative 7813 pounds. Okay, so now before I continue, I want to see if those two forces make any sense to you. We had water, it was coming from left to right, and now we have water that's doing this. Okay, so does that make sense that the force would be upwards? The force of the bend on the water. Yeah, right? There has to be some kind of push here to make it go upwards, right? And then what about this one? This one might be a little bit less obvious. Okay. But let's see, imagine you were holding this pipe. Okay, what would you expect it was going to be pushing, like, your hand? Well, it's going to be pushing on your hand to the right, so you would have to be pushing to the left to make this happen. So both these numbers make sense. Okay, so let's go ahead and finalize this equation. I'm just going to pause it, and this will be done. Okay. All right, so if we do the trig, we end up with force of bend on water equals 8.19 kips at 17.5 degrees north of west. Unfortunately, the problem asked for the force of the water on bend. So that's pretty easy. 8.19 kips, force water on bend at 17.5 degrees. Okay, so the opposite direction, equal and opposite. Okay, so there you go. So if I were to redraw this, okay, and I wanted to draw the force of the water on the bend, the water would be pushing it that way. All right, 17.5 degrees with 8.19 kips. All right, so that's this problem, and I think the other two are a little bit shorter. So we will do those in part B. See ya. Oh, I hate when it does that.